Okay, so today we're going to talk about how to graph a quadratic function and inequality in what we call standard form. So a quadratic function is another word for parabola. It's going to be our U-shaped curve, so it'll either look like that, where it's going upwards, or it will be going downwards. That's our quadratics. Technically, parabolas can also go horizontally, but when we get to that kind of stuff with conic sections much later on, we'll discuss how to graph those. So again, if you're following along in the Glencoe Algebra 2 2018 edition textbook, we'll be in sections 3.1 and 3.7, page 151 and page 205. So a quadratic function in standard form will look like this. f of x equals ax squared plus bx plus c. Whereas vertex form will be f of x equals a, and then the expression x minus h squared plus k. We'll talk about how to graph parabolas quadratics in vertex form at a later date. So again, we're talking about the standard form today, ax squared plus bx plus c. Where to graph these quadratics, we need to first find what we call the vertex point. Now this vertex point is either the lowest point of the u, the minimum value right down there, or the highest point of the u, the max value right there, depending upon which direction it's going. After we find the vertex point, we're going to need two other points to create this particular U shape. Now, the nice thing about quadratics is that they are symmetric about the vertex point. So once we know one point, we know the second point, because it has to be equidistant away from the vertex point. Now, finding the vertex point is pretty much the first step, and really the only challenging step, even though it's not really challenging, to finding the quadratic. We need to plug in negative b over 2a. So our b value, negative of that, divided by 2 times our a value, that tells us the x-coordinate of the vertex point. From there, we plug that value back into the original function. That'll tell you the y-coordinates. So if we want to graph this function right here, we again need to identify our a and b values. So a is 2, b is negative 4. That means the x-coordinate of the vertex would be negative of negative 4 over 2 times 2. 4 over 4, which is 1. So the x-coordinate of the vertex point is at 1. So then we're going to find the y-coordinates. We just simply plug in the 1 in for x. So 2 times 1 squared minus 4 times 1 plus 3. We need to make sure we square the 1 before we multiply by 2. So that's why this is going to be 2 minus 4 plus 3, which is also 1. So our vertex point is at 1, 1. So it'll be right there. Now, the second point we want to find, when it's in standard form, is going to pretty much be the y-intercept, when it's a nice number like this one right here. The number at the end of the function, the c value, will always represent the y-intercept for our quadratic functions. So we're going to cross the y-axis at 3. Now, the idea of the symmetric point is that it has to be equidistant from the vertex points. So since this is 1 to the left of the vertex, we go 1 to the right. There's our symmetric point. And again, you make your U. Try to make it a little bit better looking than that, but that's the general idea. You want to create a curve, U curve, between those 3 points. And that's our quadratic function in standard form. Very straightforward. We find the x-coordinate, the negative b over 2a. Plug in to find the y-coordinate. That's our vertex point. And then our symmetric point, we can use the y-intercept if it's a nice number. If it's not, let's say, for example, it's like 12 or 40, and it's something we don't really want to plot on our graph. What we can do is we can do two options. You can simply plug in any x value you want. Typically, you want to plug in only 1 or 2 away from the vertex point. That way it's smaller numbers. We also recognize this right here, this 2, is kind of like a slope. It's not really a slope because obviously the curve is constantly changing. But if you notice, from the vertex point, we go up 2 and to the right 1. Up 2, to the left 1, and then to the right 1. So we can use that as an approximation when we go 1 to the left or 1 to the right. Best to only use this when it's a whole number, because if it's a half, technically we have to go over 1 and up a half, and it's not really a nice point to be plotting. So keep that in mind as one quick way to go through it, or again, plug in any x values you want. Alright, so if it looks like this, our a value is negative 1, because that's what's in front of x squared. Our b value is a positive 2, because that's what's in front of x. So the x-coordinate of the vertex will be negative of b divided by 2 times a. Negative 2 over negative 2 which is positive 1. We then plug that 1 back into the function. So negative of 1 squared plus 2 times 1 plus 2. So again, we square the 1 first before we deal with the negative, so this becomes negative 1 plus 2, which is 3. So our vertex point will be at 1, 3. Again, if we use our y-intercept idea, we're going to go to 2 on the y-axis. Since that was 1 to the left of the vertex point, we go 1 to the right. Those are symmetric points. Now we connect them with the curve. That looks a little better than last time. And there's our quadratic function. Like I said before, we could have also used the idea of what the slope is, which is negative 1. So we can go down 1 and then left and right 1 to create our points. And it still works out fine. But like I said, that's not really too necessary unless we have nastier numbers to deal with for our y-intercepts, ones that don't fit nicely on our graphs. So that's graphing a quadratic function. Graphing a quadratic inequality is the same general idea. Same way like when we graph linear inequalities, we still found the same points. It's how we connect them and where we shade that's different. So remember that if it's equal to, we connect it with that solid line. But if it's just less than or just greater than, there's no equal to component to it, then it's a dashed line that we have to use to connect the points. And then shading in, well, if it's greater than, we shade in above. If it's less than, we shade below. Now again, above, if it looks this way, will be inside the curve, whereas above, if it's going downwards, will be outside the curve. So don't assume greater than always means inside and less than always means outside. It depends on the direction the curve is going. Always think of it as above and below. So if we want to graph this one, again, same general point. We find the vertex point. A is 2, B is 16. So the x-coordinate of the vertex point will be negative b divided by 2 times 2. You get negative 16 over 4, which is negative 4. And we plugged it in for the y-coordinates, so 2 times negative 4 squared plus 16 times negative 4 plus 33. We square the negative 4 first to get 16 times 2 is 32. And this is negative 64, this is positive 33. So when we combine all that, we find that this works out to be nice 1. So even though the numbers seem a little big, they've been chosen for a reason so that the vertex point should work out as a nice number. My whole goal when I'm asking you guys to graph this stuff is to make sure it shows up on the 10 by 10 grid as the absolute maximum size it's going to be, that we don't have to worry too much about it. So we go to negative 4x, positive 1y. There's our vertex point. Now for this example, using the y-intercept of 33 is impossible because our grid is only going up as high as 10, so 33 would be way off it. So here's where the approximation of slope comes in nicely. The number in front of the x-squared is 2, so I can go up 2 from that point, and I go left and right 1. If you're not 100% comfortable with using that idea, feel free to plug in any numbers you want. You'll find if you do plug in negative 3 for x, you'll get a positive 3 for your answer. So you can trust it, but again, if you're not comfortable, that's fine. Plug in points. So we just connect the points with our curve. And it's solid because it was just greater than or equal to, so we're fine there. And since it's greater than, we're going above. So that's why we're shading inside it for this particular case. Okay, so that's one of our examples of quadratic inequalities. So if we take a look at the other example, again, same general thought process. A is negative 1, B is negative 6. So the x-coordinate is negative of b divided by 2 times a. 6 over negative 2, which is negative 3. We then plug that in to find y, so it's negative of negative 3 squared minus 6 times negative 3 minus 6. Well, again, we square the negative 3 first to get a positive 9, but then it becomes negative because of the negative on the outside. This is positive 18, this is negative 6, so this works out to be positive 3. So we're going to go to negative 3, positive 3. There's our vertex point. Now we're welcome to still use the idea of slope for this because there's negative 1 in front, but we see that our y-intercept is a nice number this time. So I'm just going to plot it on the y-intercept. It's always easiest to see that. So we go down to 6. There's our y-intercept. And then since I'm going 3 to the right, I have to go 3 to the left. So 1, 2, 3. There's the symmetric points. Now for this one, because it's just greater than, we need to use a dotted line or a dashed line to create the shape. One advantage if you're using a pencil to always do these graphs, as you really should in math, is if you happen to accidentally do a solid line when you should have done dash, you can then kind of erase section of it to make it look dashed. Alright, it's greater than, so we have to be above the curve. So above the curve is everywhere out here. So that's our quadratic inequality. Alright, so that's the idea of graphing quadratic functions and inequalities in standard form. Next video we'll talk about how to graph them in vertex form. So I will see you next time.